Okay, so last week we looked over rivers and groundwater. So in our review, we'll go ahead and go back to that. Recall that last week we looked at some different types of rivers. One of the rivers is a meandering river with oxbow lakes. So what happens through time is we have a bendy river that will get bendier with time. So if we look at the mechanism of that river, in the outside bend of the meandering river, we have erosion where we have faster water velocity. And that eroded material gets deposited in the blue section. So our river becomes relatively bendier until the bends will actually touch and the river will cut through, leaving behind these oxbow lakes. So the velocity of the river channel is dependent on the shape, also the position of where you are along the river in a meandering river system or meandering bend. So on the outside bend, we have faster, higher velocity water than the inside bend where we have deposition. Also, the shape of the channel determines the velocity as well. So a steeper and deeper channel is relatively higher velocity than the inside, shallower channel. We measure discharge, so the amount of water that is moving through a river at a given amount of time through units of volumes per time. So in here we have cubic feet per second. And you determine discharge by taking a cross-section of the river. And we can do this by fitting a cross-sections with various boxes to fit the irregular shape of a cross-section of a river. Calculate our area and then multiply our area with the river velocity to determine the amount of discharge. And in groundwater, we looked at porosity and permeability. We were provided a data set of different sediment groups from silt to gravel to sands, to fine sands. And these different sediment groups had a different porosity and permeability. So what was done to achieve that data set was saturation of the sediment to measure the entire water content that would take to fill the voids of a given sediment. And then also measuring a time trickle of how much water would pass through the sediment over a given amount of time, and that would be a measure of permeability. Some controls on the porosity and permeability fronts would be the different types of grains that would be encountered and how well sorted or poorly sorted these grains are. So in a well-sorted sense, we have high permeability and high porosity. In a poorly sorted, we have smaller grains filling in the voids of the larger grains, and thus we would effectively reduce the porosity and also restrict fluid flow between the individual grains, so effectively reducing permeability as well. If we take the void spaces and fill it in with a matrix material such as fine silt or clay, we essentially create nearly an impervious layer. So we would have very low permeability and the porosity would also be fairly low as well. And now we're discussing our current week's lab, which is geologic time, or in layman's term, the dating of rocks. So in geologic dating, we have two different methods. We have relative dating and we have radiometric dating. In relative dating, we look at rocks and geologic units and also events based on the position and how their relationship to one another is in the position within the Earth. And based on that, we're able to determine a chronological order of when these events occurred, when these units were deposited. So it's kind of looking at what came first, second, third, fourth, fifth, instead of unit X is 5 million years old and unit Y is 3 million years old. To get a specific number, we go into radiometric dating. and this is where we look at the properties of half-lives of specific isotopes found in whatever unit or rock that you're looking at. And you measure these half-lives to determine a geologic age. So here we have our a snippet of the geologic time scale. And let's say based on some samples, we are able to determine some specific ages of rocks. And we do radiometric dating some more, and we're able to determine some more specific ages of specific rocks or also events. If we note that this isn't a linear process, so if we have rocks from K1, K2, K3, we can determine the relative age between them, knowing that K1 is probably the oldest, K2 is the second oldest, and K3 is the youngest. But age and depth is not linear, so we can't use depth to specifically give us an age. So if we were to dig down 10 feet, we can't say specifically that that's going to be 1,000 years old. And by that measure, we would use our geologic dating methods such as radiometric dating and relative dating. So in radiometric dating, we are measuring the ratio between daughter and parent isotopes with a known half-life. So we'd look at the percentage of parent isotopes left and determine the age based on the half-life. And we'd also compare this and use it in conjunction with relative dating to have a better estimate. However, we can't just guess with a lot of different things. There are certain laws that govern geologic processes and our geologic dating methods, such as Uniformitarianism, which assumes that the same natural laws of the process that governs the universe also applies here in geology. So what that means is when you deposit stuff, dust, sand, rocks, whatever it may be, that material settles down. It falls down and forms a nice even layer horizontally, which brings us down to original horizontality, which means sediment layers are deposited in layers, and they are deposited horizontally and evenly. Law of superposition stating that anything that is unaltered, so undisturbed rock or strata, we would have the oldest material on the bottom because it gets deposited first, and then the younger material on the top because it gets deposited last. Lateral continuity states that each sediment layer will extend out horizontally and will be undisturbed. And to continue on with the laws, we have inclusions, cross-cutting relationship, and fossil succession. So in inclusions is where we have an older rock that's caught up in a younger rock. So if you recall from the igneous lab and also the sedimentary lab, so in the igneous lab, we had our volcanic rocks. Some of those volcanic rocks had crystals or older rocks, fragments that were inside of that volcanic rock, and they were ejected out of the volcano together. So the volcanic rock itself formed when it was ejected out of the volcano. However, those rock fragments or crystal has an age date that is much older than the formation of the volcanic rock. If we look at the conglomerates from our sedimentary lab, each individual pebble has a much older age than the conglomerate rock itself. In cross-cutting relationship, this is where we have, for example, horizontal strata, so horizontal rock units and layers, and we would have a magma intrusion. So magma would cross-cut these horizontal layers. So it might cross-cut at an angle or vertically, but this cross-cutting would tell us that whatever cuts through these horizontal layers, or cuts through or breaks up a flow, will be much younger. So fossil succession states that specific groups of animals that follow one after another is will be in a definite sequence throughout the Earth. So, for example, that means that if you find a fossil of a mammal or a large mammal, it's going to be a lot younger than a fossil of a dinosaur. That's basically what that means. So in this diagram here, we have a three-dimensional cube of the Earth pulled out, where we have our rivers and groundwater up above, and then we start going into our different layers or strata of units below. From this image, we have a nice puzzle pattern in terms of trying to figure out what came first in terms of what layer and what event. So if we see from A to T, A was deposited first, then B, then C, then D, all the way to G. The whole event, the whole section was tilted 45 degrees. There was an erosional event, that was I. JKL was deposited. There was a erosional event again. M came in. Oh, my apologies. It looks like M came in first and then the erosional event, and we could tell that based on the inclusions of the magma body at the very top of M. And then we have the following depositions before we have cross-cutting of event R. In unconformities is pretty much a gap of time that is missing. So this could be due to a disconformity, angular unconformity, or a non-conformity. So these are three different types of unconformities. A disconformity is where we have horizontal layers, and then there is just a chunk that is missing. So in the previous example, we had A, B, C, D, E, and F all the way up to T. If all those layers are horizontal and we're missing everything from H to M, that would be considered as a disconformity, where all the different layers would be still horizontal, but we'd just be missing a specific gap of time in between some layers. An angular unconformity is where we have some tilted layers, and those tilted layers are eroded, and we have new deposited layers that are nice and flat and horizontal on top of the tilted, eroded layers. A non-conformity is two very different types of rocks that would be in contact with one another that wouldn't really make sense. So for example, if we had a intrusive igneous body rock such as a granite, and we have sedimentary type rock that is right up against it in nice flat horizontal layers, the contact between the sedimentary rock and the igneous rock would be a non-conformity. So the example here, we have a lovely rock outcrop next to the ocean. We do see that there is an angular unconformity. If we can see that there are some particular lineation that is moving in an up-down direction up towards that red line, and then that red line is parallel to the rock units that are above it. So let's remember that unconformity is a gap in time. So it's shown here that in the image to the left, we have older strata and younger strata in there. And in between, we have an erosional event E. Erosional event E has scrubbed out a unknown amount of geologic time. We don't know what's the age gap between the older strata and the younger strata, because apparently this is through relative dating. Since no specific age is given, we can just infer that it is the bottom layer is older and the above layer is younger. So if we look at our disconformity on the right, we have labeled units A, B, C, G, and H. So G and H are certainly the younger units, and that dark black line is our erosional event. So that is also our disconformity. based on the labeling, we can infer that D all the way to G has been eroded, and we have lost that amount of geologic time.